I'd like to take a look at all four of these reactions here and see how the values for delta H and delta S for each of these four reactions vary, and how the values of delta H and delta S help us determine whether the reaction will be spontaneous as written or not. Now, the first of these equations you should recognize. We've talked about this equation a lot. We've got glucose plus oxygen going to carbon dioxide and water. That's respiration. And if I look at this, I see I have a mole of a solid, 6 moles of a gas, going to 6 and 6, that's 12 moles of a gas. So do you think delta S for this process is going to be positive or negative? What do you think? Well, stuff is going to more gaseous form, so our delta S is going to be positive. It's going to a more probabilistic higher entropy state. We also know that this is a combustion reaction, and combustion reactions tend to be exothermic. They release energy to the surroundings, so delta H is going to be negative. In both cases, the delta H and the delta S, they both favor the reaction. So we see delta H negative, delta S positive. These both favor the reaction, and so respiration is going to be favored at all temperatures. It just goes. There's nothing you have to do to make the chemical reaction of respiration go in your body. It just does. Now let's look at the reverse of this. What is the reverse of respiration? Well, it's photosynthesis. This is the second reaction here. 6 moles of carbon dioxide and 6 moles of gaseous water go to glucose, solid glucose, and 6 moles of oxygen. Well, that's going to be the opposite. The entropy here is negative. We are going from gaseous substances, 12 moles of a gas, to 6 moles of a gas and 1 mole of a solid. That's an organization of matter. Less probable, so the entropy is negative. The enthalpy will be the opposite, right? This is the opposite of combustion, so our delta H there is going to be positive. In this case, both of these do not favor the reaction. This does not happen on its own. Photosynthesis does not happen on its own. There's a reason why plants need to take in energy. Plants need to take in energy to drive this process, because this process doesn't happen by itself. And so that's why plants take in sunlight to drive this particular reaction. Now there's two other reactions here that we want to look at that give us different combinations of delta H and delta S. Let's look at the first one. Let's see, this is the freezing of water. Well, this is representing some random liquid molecules going to organized liquid molecules. I think that represents a delta S that's going to be negative, an ordering of matter, a lower probability. Delta H, on the other hand, we're going from high energy liquid molecules to lower energy, less kinetic energy, solid molecules. So this is going to represent an exothermic change. So that's going to be negative. So in terms of the enthalpy, this reaction is favored, but in terms of the entropy, it is disfavored. Well, let's see, does this tend to happen at higher or lower temperature? Because, we got to figure out what's going to go on here, and the temperature is going to be the arbiter of whether this reaction is going to be spontaneous or not. And let's see, I happen to know that if I want to freeze some water, I'm going to put it in the freezer. So the case where both of these have the same sign and they're negative, this tends to be favored at low temperature. Now we'll take the opposite of this process here. In this case, we have solid water going to liquid water. That is the case of melting. In terms of the entropy, we've got matter being disorganized or spread out or sent to a more probabilistic state. So my entropy there is going to be positive. We go to a higher probability, more free state. We go from a solid to a liquid. However, we recognize that we have to put energy into this system. Energy that's randomized out in the surroundings has to get concentrated into the system in order for it to go. So my delta H there, that's going to be positive, and this is going to be disfavored. So in this case, the entropy favors the reaction, but the enthalpy disfavors the reaction. And we recognize that this happens to be favored. If I want to melt some ice, I raise the temperature. So in the case where both of these are positive, but they're, opposed to one another, one is favoring the reaction and one is disfavoring the reaction, this happens to happen at high temperature. So we have our 4 cases here, 4 possible cases and 4 examples. The example where both the enthalpy and the entropy favor the reaction, so the reaction goes at all temperatures, that is going to be represented by respiration. That's an example we can sort of sink our teeth in to remember this. An example where both the enthalpy and the entropy disfavor the reaction, well, that's going to be photosynthesis. And this is non-spontaneous at all temperatures, and this is why plants have to take in energy to get this reaction to go. Then there are the 2 cases. If the signs are the same, this ends up being a case where one of the thermodynamic functions favors the reaction. In this case, the negative enthalpy favors the reaction, but the negative entropy disfavors the reaction. And when both of them are negative and they're opposed to one another, and what's going to happen, the reaction tends to be favored at lower temperature when both are negative. And when both signs are positive, again, both of these oppose one another. In this case, the entropy favors the reaction, but the enthalpy disfavors the reaction. And reactions that show this particular characteristic tend to become more favored at higher temperatures. I'm going to go over these 4 cases of combinations of delta H and delta S, and how those 4 cases help us determine the spontaneity or the sign of delta G. So our 4 cases are delta H and delta S can both be positive. Delta H and delta S can both be negative. We can have the case where delta H is positive and delta S is negative. And we can also have the case where delta H is negative and delta S is positive. Under these 4 conditions, what will the sign of delta G be? Well, let's look at this first case. What is the sign of delta G going to be when delta H is positive and delta S is negative? Well, notice when I do the math, I'm going to take a positive number and then I'm going to subtract another positive number. So what this means is, because a negative, this is going to be a negative times a positive times a positive ends up being a negative, right? And this portion is controlled by the temperature. So I'm going to take this negative and I'm going to multiply it by temperature. So as the temperature gets higher and higher and higher, the negative gets bigger and bigger and bigger. So what we see is, as at low temperatures, my delta G is going to be, well, if this is 0, my delta G is going to be positive, right? But as my temperature increases, the negative portion gets bigger and bigger and bigger. So at some high temperature, this is going to become, well, it's going to become negative. So delta G is positive at low temperature, but delta G is going to be negative at high temperature. Now let's look at this second case. Once again, my delta H will stay negative, but I'm gonna multiply my negative delta S by a negative. And a negative times a negative, well, that is a positive, isn't it? And remember, I'm going to take this positive, I'm going to multiply it by temperature. So in the case where, we'll say delta G at low temperature, we'll just make this 0 to make it easier on ourselves, and then we get to ignore it. Delta G will be delta H at absolute 0. So at low temperatures, delta H and delta G will have the same sign, because delta G will be the same as delta H. So delta G will be negative at low temperature. But as we get to higher and higher temperatures, we're going to have to start adding a bigger and bigger and bigger positive. And at some point, that temperature is going to get so large that the positive will overcome the negative. So delta G here is going to end up being positive at high temperature. So it's the opposite. And again, just so you remember, this is getting a little messy here. Let's just do this over here, delta H and delta S. This is the first case where they were both positive, and this second case was the case where they were both negative. Now we can look at this particular case, the third case. I'll just write it over here. Positive delta H and a negative delta S, and a positive delta H, a negative delta H and a positive delta S. All right, in this first case, we're going to have a positive delta H, and we will be subtracting a negative. So it'll be a negative times a negative. Well, negative times a negative, that ends up being positive, doesn't it? So look at this. No matter what, it doesn't matter what the temperature is, delta H is always going to be positive, and the contribution of delta S to the Gibbs energy is also going to be positive. So under all cases, delta G is going to be positive. So the case where delta H is positive and delta S is positive, that is always going to have a delta G positive. It's always going to be delta G positive, and it's always going to be non-spontaneous. Of course, the opposite is probably going to be true here. Let's just check it out. Delta H is negative, and then we're going to subtract a positive. So a negative times a positive, that ends up being a negative at all times, doesn't it? So we're going to have a delta H term that's always negative. We're going to have a T delta S term that's always negative. A negative subtract a negative, that's always going to be negative. So the case where delta H is negative and delta S is positive, that's always going to end up having delta G negative, and it's always going to be spontaneous. So the top two depend on temperature. The bottom two in this particular case, those are going to always be non-spontaneous in this case and spontaneous in this case. Now let's take this reaction here. Let's take a reversible reaction like liquid water. We'll make it go into gaseous water. And this is one of those cases where it depends on temperature. So let's see, which case is it? Is it case 1 or is it case 2? Is this a case where delta H is positive and delta S is positive? Or is it the case where delta H is negative and delta S is negative? Well, I think it's the first case, right? Because we're going to a more probable state. Stuff's more spread out, so delta S is positive. And of course, we got to put energy as heat into this to get it to go, so delta H is positive as well. And we see that whether this is spontaneous or not, in this direction, it depends on the temperature. It's going to tend to be more spontaneous. It should make sense at high temperature, right? I mean, that's what you got to do to get water to boil. But we can actually see this in a couple different ways. What I can do is I can write, okay, so if delta G is negative for this reaction, that means it's going to proceed in this direction. Well, that's kind of interesting. That must mean if delta G is positive, then overall it's going to proceed in this direction. Well, what if delta G is 0? Well, if delta G is 0, then the system be at equilibrium. It's not overall going to look like it's proceeding in either direction. It's just going to stay with the same amount of liquid and the same amount of gas in the system as time proceeds. So that allows me to do something interesting here. What I'm going to do is I'm going to plug in 0 for delta G in this equation. This is going to allow me to do something kind of neat. So I can write 0 is delta H minus T delta S. And I'm going to add T delta S to both sides of this equation. And if I do that, this cancels. And I get T delta S is delta H. I divide both sides by delta S. And I get this equation that says temperature is delta H over delta S. What the heck does that mean? Well, in this case, this temperature represents an estimate of the temperature at which this process is at equilibrium. Well, what is the temperature at which this process is at equilibrium? Hey, that might be the temperature at which water boils. I wonder if that'll work. Let's try it out. So let's see, what was I going to do? I'm taking liquid water, and I'm looking at it going to gaseous water, of course in a reversible fashion. And I want to look at the temperature estimate at which this process is at equilibrium. So I need to know what delta H is for this process, and I need to know what delta S is for this process. So I think I'm going to need to look up some thermodynamic values in Appendix L. Let's see, I need my delta H's for liquid water. So let me just write delta H here. That's going to be negative 286. and all of these are kilojoules per mole. So I want to make sure I got this right. This is H2O liquid. And then for the gas, that's going to be minus 242. And then my delta S, this is joules per mole per Kelvin. Pay attention to that. Yep. And so for the liquid, it's about 70. And for the gas, it looks like it's 189. We've seen these numbers before. I'm going to use them now. Okay, so now I can figure out what my delta H is for the process. So let's see. Delta H, that's going to be the final enthalpy minus the initial enthalpy. So what's that going to be? Final is H2O gas. That's negative 242 minus the initial, which is my H2O liquid, a negative 286. So I'm going to have to add that. So my delta H for this process, what's that come out to? What's that? 286 positive minus 242. That looks like a positive 44 kilojoules per mole. Okay? Now let's check out my delta S for the process. Well, that's going to be my final entropy minus my initial entropy. So let's see, what's that going to be? The final is 189 for the gas. And this is joules per mole Kelvin. Let's make sure I did that right. Yep, gas. And then my initial enthalpy, that'll be the liquid, how I started, minus 70. That's 119 joules per mole per Kelvin. So this is my delta S. This is my delta H. Let's plug it into here. Temperature, that should be, I better make sure these talk to each other. I think I'll change this to joules. So it's going to be 44,000 joules per mole. That's my enthalpy. And I'm going to divide that by 119 joules per mole per Kelvin. That's going to be my change in entropy for this particular process. I'm getting kind of excited here. I hope this works out. Okay. So let's see. Joules cancels joules. Inverse moles cancels inverse mole. I have an inverse Kelvin on the denominator. That's a Kelvin temperature. So let's see. 44,000 divided by 119. 370 Kelvin. That's not a bad estimate. Does anybody happen to remember what the boiling temperature is of water in units of kelvins? It's 373. That's not too bad of an estimate, isn't it? That's not too bad. You ought to try this for this process. Let's see what you come up with. Anyone remember what the equilibrium temperature for this should be? Well, when you do it yourself, you'll know if you got it right or not, if you can remember what that temperature ought to be.